In Zoom class today, we talked about some of the consequences that follow from making the assumption that the axiom of completeness is a true statement. In particular, we talked about how the natural numbers and how the rationals sit inside the reals. So the Archimedean property was talking about how the natural numbers sit inside R, and then the density of Q and R is telling us that the rationals sit densely inside the real line. There is one other major theorem in this section, and it's called the nested interval property, and that's what this video is devoted to. So the nested interval property is just another way to say that the real line has no gaps. We said that the axiom of completeness, that what it's saying high level is that the real line has no gaps. Well, it turns out that if we assume the axiom of completeness is true, then we're able to prove the nested interval property holds. But I could alternatively assume the nested interval property is my axiom, and that would actually enable me to prove the statement in the axiom of completeness. They're equivalent assumptions that can form the foundation for the real number system. So in reading what it says, it's probably not immediately clear why this is talking about no gaps in the real line, but I'll take you through an explanation that will hopefully clarify that for you. So the nested interval property, first of all, assumes that you're working with these intervals, I sub n. So for each natural number, we're going to define an interval, and that interval is a closed and bounded interval. So it includes its endpoints and it has finite length. An here is a real number that's assumed to be strictly less than bn. So here, i.e. each in is a closed and bounded interval. And then the second property is that I1 contains I2 and I2 contains I3, etc. This is what we mean when we talk about nested intervals. So that explains the title of this theorem, the nested interval property. So here we're saying that if we have these closed and bounded intervals and they're nested, when you take the intersection of all of them, they are non-empty. Now, we've previously seen that the intersection of nested sets it is possible that it could be empty. You should have seen that in working on your homework, in homework 1, and then also I went over an example of intervals from 0 to 1 over n in the set theory review video. But it turns out that if you get to assume that your sets aren't just nested, but that they're closed and bounded intervals, that's enough to guarantee that something is always inside the intersection. So a question you might ask is, what the heck does this have to do with asserting that the real line has no gaps? Well, one way you can think of it is the nested interval property is giving us a way to zoom in on the real line. The nestedness is creating that ability to zoom in. Each interval you select, when you go to the next interval, you either have the same interval or you have a smaller interval that is zoomed in inside that one. So what I mean by this is, let's say that this is my I1. And then I2 moves in a little bit more. And then I3 continues. And I just keep going. Zooming in, shrinking with my intervals. And what I'm saying when I say that the real line has no gaps, when I plot all of those real numbers, what I should see is that there is no hole here. Now there would be a hole there if the hole would happen if the intersection of all of these intervals was empty, because that would be our way of saying the one thing that's in the middle, well, there isn't one thing in the middle. The intersection is empty, but we're asserting that that can't happen. This is no hole because the intersection of all my INs is not the empty set. If it could be empty, you would be finding a hole. So that's what it means, or why it means that the real line has no gaps. So we're supposed to prove that the intersection of the INs is non-empty. And the way you do that is you find a candidate X that's in every set and you show it's in every set. So you show that you actually have a value that meets the conditions of being a member of the intersection, and then it's non-empty. But that begs the question, what is X? If I'm going to prove this intersection of intervals is non-empty, I need a candidate. So let's take a look at some examples here. I've given you two different nested sequences of sets. We've got IN and we've got JN here. Let's take a look at what their intersections are, and then maybe we can think about what we would expect in general to be always in the intersection, regardless of what closed and bounded nested intervals you're looking at. So the intersection of my INs, the only thing in common with all of the sets is 0. If you think about what these look like, your first set is -1 to 1. Then you're going to zoom in and go -0.5 to 0.5. You're just getting closer and closer and closer, and what you're zooming in on is 0. Over here, the intersection of the JNs is similar, behaves similarly, but rather than zooming in on a single point, we're actually zooming in on an interval, and the interval you're zooming in on is 0 to 1. So here you are, 0, 1, 2. If you look at what these sets look like, the first one is 0 to 2, the next one is 0 to 3/2, and then you just keep going, and you're eventually zooming in on that interval 0 to 1. So we're trying to figure out, given an arbitrary interval a n to bn, how do we know what x we should always try to say? Like, how does x relate to an or bn such that we can always claim that in general there's an x in the intersection of these intervals? What I want you to do is to pause the video, and I want you to focus in particular either on the left endpoints or focus on the right endpoints, and ask yourself, how is the intersection related to what's going on with those? Now, if I go and I focus, say, only on the left endpoints, then I've got my first left endpoint at -1, then I'm moving closer and closer and closer to 0. And so those left endpoints are getting tighter and tighter against the number 0. If I were to just plot these points, I would have -1, -0.5, -1/3, etc. And I'd be getting closer and closer and closer, zooming in, towards 0. Now, if you recall the name of section 1.4, it's called the Consequences of Completeness, which means all of the results that we're discussing in this section are results that can be proven as a result of the axiom of completeness. If you remember, the axiom of completeness is a statement about the existence of a supremum, or a least upper bound. So what we might ask is, in this example here that I've drawn out, how is this related to supremums? Like we said, pay attention to the left endpoints. What if I did only the left endpoints over here? If I did only the left endpoints over here, I would have literally just one point in my set. So how is this related to sups? What set am I talking about? So we're saying A is all of the ANs. That's the set of left endpoints. And we're asking, what's x such that x is in the intersection? Well, it looks like in this picture up here that this is the soup of my A's, my set A. And this is also, over here, my set A is just literally the point zero. There's only one left endpoint. The soup of that set is zero. So our claim is that X equal to soup A, where A is the set of left endpoints, is such that X is in the intersection of the INs. And that's what we want to prove. Now, before we can even start trying to see whether or not the soup is in the intersection, we have to explain why the supremum exists. So, why does soup A exist? Okay, so we said the axiom of completeness is our theorem that explains the conditions under which a supremum exists. The first is that A has to be non-empty. So let's look at our set A. Remember what our set is. It's the set of left endpoints. Well, it better be non-empty because otherwise we're not working with intervals. We're told we have intervals, which means we have left endpoints. In particular, for example, A1 has to be in A. The first set has a left endpoint. And then the second condition is that A has to be bounded above. Now this one is less obvious. Let's look at our picture back up here. These left endpoints need to be, they're getting closer and closer to zero. We're talking about the soup of that. We need upper bounds for all the left endpoints. If I look at my picture, what I see is that every single right endpoint lies to the right of those left endpoints. So it turns out that A is bounded above by any right endpoint. Could be B1, could be B2. In general, it's just some B sub n. Now, looking at the picture, it seemed more obvious, like for this particular example, but how would I show that each Bn bounds the set A? We need a proof. Well, suppose Bn is not an upper bound for A. Well, what does that mean? The set A, remember, is a set of left endpoints. So if you're not an upper bound for a set, it means that there's got to be a number in the set. So there exists some little a in it, capital A, such that A is bigger than Bn. So here, an element of my set A looks like a little a something. Now, I don't want to call little a, I'm going to call it some little a I. Now, the reason why I didn't call it an is because the AI that I get from my set doesn't have to be from the same corresponding interval. If I were to use n, then it would an, I'd be in particular, I'd be using the left endpoint of the same right endpoint that I'm trying to show as an upper bound. So this is for some I in the natural numbers. We need to figure out why this is a contradiction. Right now what we said is, here's our Bn, and we're claiming that we can get some other little ai that's bigger than it. So we ask ourselves, what is wrong with this picture? So I would pause and try to figure out if you can understand what's wrong with this picture. What I suggest doing for this is to draw the other halves of the intervals. If I'm talking about Bn, that has to have a left endpoint associated with it. And if I'm talking about AI, that has to have some right endpoint, Bi, associated with it. And so here, this is my interval I sub little I, and this is my interval I sub n. And we're asking, what's wrong? You should see that the issue is that these sets are not nested. So by definition, IN intersect I little I, that's got to be, the empty set. And the intervals aren't nested. But that contradicts our assumption, because we're talking about the nested interval property. We assume that our intervals are nested. And since we have a contradiction, that tells me, remember, we had assumed Bn was not an upper bound. That means that Bn is an upper bound. So what we're saying is that for all little a and a is less than or equal to Bn. That means that the second condition of the axiom of completeness holds, so we can say, therefore, by the AOC, X exists, or sup A exists. And then we're going to let X equal sup A. And we want to show that X is in the intersection of all of the INs, which really means we need to show X is in IN for all n. Well, what does that mean? If X is in an interval, that means that it satisfies the inequality associated with that interval. So this implies that AN is less than or equal to X, which is less than or equal to Bn. And we need to show this for all X. For all n. So that gives us two inequalities that we need to demonstrate. So we want to show AN is less than or equal to X for all n. And we want to show X is less than or equal to Bn for all n. And all we know right now is that X is the sup. So I would pause and think about how you might do this. Okay, so the first part of the definition of the supremum tells us that X is an upper bound for A. And the second part tells us that if little b is an upper bound for A, then x has to be less than or equal to b. That's just the definition of soup. Well, let's look over here. X is an upper bound for A. I claim that is exactly what this statement says. That's because, remember what we wanted, being an upper bound up here, we said for any A in your set, A is less than or equal to that upper bound. Well, this is the definition of X, an upper bound for our set A. So that's true. And then we want to show that X is less than or equal to Bn. But remember, X is the supremum, and we know that as long as we have an upper bound, X has to be least. So this is true since Bn is an upper bound. We've already shown that. We just showed that above so that we could apply the AOC. So X is the least upper bound. Well, we've shown that AN is less than or equal to X for all N. We've shown that X is less than or equal to Bn for all N. X is in the intersection for all, or it has to be in IN for all N. So X is in the intersection. And if you have something in the intersection, you're non-empty. We can say that our intersection is non-empty, and that's exactly what we wanted to show.